First of all, you think that your reaction P might be pushing up. Second of all, okay, whatever you want to assume, okay, moment, okay, just assume this way. As long as you are consistent in the calculation, whatever you assume will lead you back home. The third thing, back to the shoreline. The third thing you have the load. Okay? Previously you just deform your system, but right now you don't deform it, but you have the load. So you have this system, P reactions here, F reactions there, and your load. W, okay? P cause this one downward, this one PL. If you want to find the theta, well, it is what? PL over 2EI. If you want to find delta, it is PL square, right? Oh, this is PL square, this is PL cube over 3EI, right? That is taken from the last classes before. This one you have the reaction M, you don't have the counterbalancing force because you don't apply any force, you don't have the reaction force. Theta equals to ML over EI, and then the delta equals to ML squared over 2EI. We know the direction of it. Okay, so we're gonna put it with the direction later. Right, so how's about this one? This one produces you the deflection like this, okay? This one is like this one is like that, right? So let's take a look at this one a little bit, because we have done this, not done this one. So the bending moment diagram, how does it look like? Negative moment, right? Equals to, what is this? WL squared over 2, right? For the moment at this location. Reactions over here, you need the W multiplied by L to balance sigma Fy. This one, WL squared over 2 to balance your moment in equilibrium. Alright, so that's all it takes. You come up with the BMD like so. As your cross section is uniform. Okay, we are talking about the basic case, so we have uniform cross section, then your curvature diagram is just gonna look like this, but you're gonna have the EI as the denominator, just that. Okay, we need the theta first. What is the area of this one? 1/3, right? 1/3 of this one. So turns out to be WL cubed over 6EI. Right? 1/3 to this one to L. And then the delta is equals to this area times this centroid, which locates at 3/4 of L. I can prove, but I don't want to spend time to prove. Okay, why 3/4 of L, why 1/3, okay? But if you just go back home, play with the polynomial functions a little bit, and then you will find that. Let's see. So this one multiplied by 3/4, you get 3 cancel with, and you get WL cube 4 over 8EI. 3 cancel with 6, you have 2 to 4, you get 8. Okay. Right. Now, let's fly up high. Look at the problem from the bird's eye view. What's next? I think maybe I should stop sometimes like this and then give you some minutes to think what to do next. Any idea? Some light at the end of the tunnel? Or is it dark now?
So, in your basic case, we consider the CT distance from the support. So now we are considering from the opposite. This is 3 by 4 into L.
This is what?
The central distance. 3 by 4 into L.
3 by 4 to L,
But in our previous case of beam, we considered the CT distance 2/3 of L. So which was from the
The 2/3 of L is because your centroid of the triangle locates at 2/3 of L. This is parabolic shape, okay? So parabolic shapes, if you find a centroid, you're gonna get the 3/4 L.
Yes, I got the point. So if for the triangular shape, it will give 1/3 of. Okay, I got the point.
Alright, okay. So from this point, can we go to the target? What do you need to find? Maybe at this point, let me ask the question. What do you need to find? After this long derivation, what do you need? You need reactions. Okay? Alright, you need reactions. Can you find reactions? What are reactions? Okay? What are reactions over here? P and M, right? Just P and M. So now, can you find reactions? Yes, right? Sometimes we should stop just like this to question ourselves. What are we doing? Okay. You're not just like, okay, mathematics so much, okay, follow him. Oh, okay, I get something, and then so you need to determine the P, you need to determine the M. That's it. Okay. Now you have used your equilibrium equation of moments and of the vertical force. Two equations has been used already in order to find out these reactions. Okay. So the next step, we need to introduce two additional equations. That is a condition that is whole in order to get this case. So theta P plus theta M plus theta as the effects of the F, well, if you call W, right? This one, 0, right? So we just change the condition. For this time, you don't have theta plus theta equals to U1 or U2, okay? Not anymore, because you don't allow any deformation at the nodal point. You are not finding the stiffness. And the next equation that is right. Zero displacement, zero rotation at the support. Alright. Just this. Okay, so first, theta, knowing that the P produce upward, the M produce downward, this one produce Okay. So first condition, PL square over 2EI if you want to keep this positive, and then minus ML over EI. Oh, just sometimes you might get confused why this one is positive. I just set up the equation, so as long as whatsoever sign convention I use, okay, this equation I gonna get the right solution. Okay, so this one, okay, you say that it is clockwise, why it is positive there, okay, you put it as positive and negative negative, or negative and positive positive, you end up with the same thing. All right, ML EI, and then what next, minus the WL cube over what, 6EI is equals to 0. Okay. Then let's work on this equation, cancel out EI. Okay, our L taken out, this is square. So I say that maybe my PL is equals to 2M plus WL square over 6. Let's make it 2M and over 3. Okay. Right. First, now you represent the P in terms of M and W. W, is it known? It has to be known. If you don't know W, okay, you don't know anything, right? Okay, so that is known. So the only unknown we have over here, P and M. Then come to the next equation. The next equation, delta P, delta M, delta W. Okay, delta P is what? PL cubed over 3EI minus ML square over 2EI. And then minus WL to the 4th over 8EI equals to 0. Cancel out, cancel, and then square EI. Now we represent the PL in terms of these things. Okay, so wow, we have minus M over 2 still there. This plug in here, I get the 2/3 of M plus WL square over 9, this guy, and then WL square over 8 equals to 0. Right? And plug these term into here. So you get 2/3, WL square over 9, this one from here, and this one from here. Okay, 2/3 of M minus 1/2 of M, what do you get? 2/3 minus 1/2, 4/3 minus 3/6, 4/6 minus 3/6, you get M over 6 equals to WL square 1/8 minus 1/9. You end up with WL square over 72, right? 1/8 is 9 over 72, 1/9 is 8 over 72, okay? You get 1 over 72. Moment is equals to WL square over 12, right? 6 and 72, 12. What is a P? You plug M back in here, you get the WL square over 6 plus WL square over 3. 1/6 plus 2/6, okay? Then 3 over 6. P is equals to WL over 2. 3 over 6, right? Now, you integrate everything up. You have P pushing upward, no point force, no point force. So for here, you have the WL/2, okay? No moment here at the tip. One moment M equals to WL²/12. No moment here. So over here you get this one WL²/12. Right? What's next? P downward. Okay. WL upward. Just these two. So P equals to WL/2. WL is WL. So these two cancel out. You have only WL/2. Remaining PL, M, and WL²/2. Okay. PL is going this way, M and this. Okay, so you have the M being the 112, and then plus 1/2. All right. This is WL²/12. This is a half going to the same direction. PL is P is WL/2, so that is also a half, right? WL². So cancel, you end up with just WL²/12. And here's how you come up with your fixed end moment. Alright, fixed end reactions. So WL/2, WL/12, etc., etc. Oh, this is just 9/7. You feel like forever. You have another half to go. Okay. I think I saw that day who gave me the rulers. I borrowed, oh, but you don't have it today, right? Let me look around for a ruler. A long one. Which ruler should be tortured by me? Okay, honey. Thank you. So essentially, in one system, I will talk more about the other, but in one system, first class, you have the ruler stay like this, and I start torturing it by deforming the ends, right? So right now, with the stiffness matrix, and then I torture it this way, we know how much force and moments at each node, right? We have that relationships derived through the stiffness matrix and through the relationships, through the also the U1, U2, U3, U4. Okay, start with U1, U2, U3, U4. Okay, so you apply all 4 U's. Okay, and then break. Okay, now what we are trying now is to put the loads in between. So if you imagine you go back home, find the rulers, okay, and then you deform it this shape, and then you ask maybe your friends to push the force, okay, whatever kind of force, distributed force or point moment, why you are keeping this 4-degree freedom stationary, okay? So the 4-degree freedom still there, not changing, but your hand's gonna feel more force and more moment as a result from the applied external force. Okay, so these two things adds up at the support. First thing is from the material deformation, okay, from the strain that is caused by the deformation at the DOF. And another thing is from the externally applied load, which does not rotate your joint anyway, but it increases your joint moment and joint force. Right? Thank you. Okay. So let's do something a little more. What if change into this form? So your W as a function of x equals to W x over L. Okay. Same concept applies, right? So you break things into three, okay? And then this one has to change. The other equation still holds. So what's going on? How much moment occurs over there at the support? You have uniformly, not uniform, the linearly varying force, okay? Your linear force this way, the centroid, if you want to calculate the centroid of this total force, the centroid will locate L over 3 from the support, right? The triangular shape, so the centroid is L over 3. How much force you have applied over here? WL over 2, okay? WL over 2 times the L over 3 as the distance from centroid. You end up with WL squared over 6, right? The distribution here, if I ask you, can you draw this distribution? Can you write the distribution of this force, this bending moment diagram? The distribution actually it is what? Cubic distribution, right? This is linear. Okay, bending moment is the linear function times the linear parabolic. No, it's supposed to be the cubic. Or to force is the square. Force is quadratic, right? If you talk about force at the point, it is quadratic shear force, and then cubic distribution. Okay. All right. If you want to draw, really, you can set up the x-axis, okay, pointing somewhere, okay, to the left, to the right, depends, okay, and then you just take a cut. Once you have a cut, you have the triangle, okay, and then you have the point force and moments. So you can do it that way, and then you end up with the distribution, which is the cubic distribution for this one. All right. Now, you want the theta. Theta is this, as it is cubic, you have 1/4 multiplied by this one. y1 over 4. Okay. X, y. You have some sort of polynomials. I don't know. I don't care what this is. One polynomial. Function of y. Y is a function of x equals to x to the n. Okay. Right. Zero to a. Let's say area come from integration of this function with respect to x. So if you integrate, then area is equals to x to the n plus 1 divided by n plus 1, right? So if you start from constant, n is equals to 0, alright? N is equals to 0. So that constant, your area will be equals to x equals to 0 to a, right? So 0, you plug in here, you get 1, alright? X, you plug n0, plug in here, you get x, evaluate from 0 to a, turns out to be a. And then the constant in front of the x, okay, which is the magnitude of this uniform function, okay? So you end up with the area of the rectangle shape. Next, if your function is the linear function, okay, then n is equals to 1. You plug in 1 to here, right? You get a half, okay, a half multiplied by this thing, okay. Well, let me check a little bit. I should break this into the form that is easy for you to understand, right? Integrate this, you get square of this, okay, which is equals to a times the, I put some coefficient k up here, okay? Put some k over here. So integrate, you will get kx, this one, and then k to the n, okay, divided by n plus 1, okay. So that makes things easier for you to figure out. Okay. I push 1x downward, okay, to here. The rest of the things are in there, n plus 1 there. So start from rectangle shape. Rectangle shape, this is the base. When n is equals to 0, you just get the k. K is that constant. Because k times the x to the 0, power of 0, that turns out to be just 1, right? So this y value is equals to k. So if you integrate, you get k multiplied by a. That's it. That's a rectangle shape. Triangular shape, n is equals to 1, so 1, 1, okay? Here is 2. You get a half multiplied by a alone is the base, right? And ka is the, here is equals to ka, right? The base is equals to a, so a half multiplied by ka multiplied by the base, okay? That's your area of triangle. You move upward, so you have quadratic function. Quadratic functions, then you get the ka squared, right? The magnitude over there is the Ka square. Here is still the A. Plug in quadratic function n turns out to be 2. 2 plus 1 you get 3. Okay? So you get 1/3 multiplied by A as the base multiplied by Ka square, which is the height. Okay? And so on and so forth. So you have the cubic function next, then you get 1/4, okay? 1/4 multiplied by the base multiplied by the height. Again. Now if you want the centroid, okay? The centroid of the area, how do you obtain it? So if you refer the centroid to this line, and then you have the centroid is the way you take the moment of the area. So you take this area dx, okay? The height is equal to kx to the n multiplied by dx. And then if you take the centroid refer to this line, here is your x, alright? So moment arm multiplied by the area being kx to the n multiplied by dx. This is the moment contributed by this infinitesimal piece of your area. You have the moment of the area already. Divide by your area. You get the centroid, the x bar. Okay? So the area which is given by the A, Ka to the n, divided by n plus 1, equal this one, right? A where is another x missing, right? Kx to the n multiplied by x, so that will be n plus 1, right? Integrate this, you get kx to the n plus 2 divided by what? N plus 2. You evaluate this from x equals to 0 to a, and then all divide by a to the n, n plus 1. So your x bar is equals to K A, okay, to the n plus 1 okay, a square, alright, divide by n plus 2 multiply by n plus 1 divided by a Ka to the n. Cancel things out, cancel out, cancel out, cancel out, cancel out. So x bar is equal to a times n plus 1 over n plus 2. Just like this. So let's start from rectangle shape. Rectangle shape, n is equal to 0. So your x bar is 0 and 0, you get a half of a. Centroid locates at the middle of the rectangle. Okay? Alright, rectangular shape, centroid is at the middle. How's about the triangle? N equals to 1 and 1. Your centroid locates at 2/3 from this point, right? 2/3 of A. How's about the parabolic shape? N equals to 2, 2 and 2, you get 3/4. Okay, so parabolic then a little more 3/4 of the A, and so on and so forth. Okay.
You know the value of n.
Hmm?
Value of n.
You know the function. Rectangular function n is equal to 0. Triangular, linear, 1. It's a polynomial. Right? The degree of polynomial. So for this one, if you have this load, right, which is distributed like this, so you cut at any location x. Okay. First of all, you need to determine the magnitude here, which is given by what? W multiplied by x over L. This is your magnitude at the point. If you want to find the area, okay, the area is equals to a half multiplied by magnitude at the point multiplied by the base, which is x. Now you get the force that is contributed by this triangle, okay, equivalent point force, and then from force you will need the moment. So you have the centroid of force multiplied by the moment arm, which is another function of x. Alright, so you have 1x, you have 2x, and then you have another x from the moment arm. That makes the cubic function out for this curve. So you know that it is cubic. Now you know it's cubic, then okay, you can determine this one, okay, you can determine by hand, but for the centroid, for example, or for the area, as it is cubic, then you know that it's gonna be the 1/4, right, multiplied by the WL square over 6 multiplied by L. So you get WL cubed over 24 as a result. And then when you want to get the delta is basically this area times the centroid from here to there, and this distance as you have the cubic function, right? Then you're gonna have 4 over 5 L over here. Cubic function n equals to 3, 4, right? 3 plus 2, 5. Okay, so you get 4 or 5. So 4 or 5, 4 cancel with this, you get WL to the 4th over 30. Right? Mm-hmm. 4 to 5, 4 cancel with this, 6 to 5, 30. Okay? Now, I push you in the water again.
So can I explain the 1/4 of W equal?
1/4. This function is cubic function, right? Cubic function, you can calculate this magnitude. Okay. So you know this one how it come from. Okay. So if you have cubic function, then to obtain the area, you get the base multiplied by the height divided by cubic, which is 3 plus 1, so it is 4. So that's why you get the factor 1 over 4 over there. Okay. Now you set it back into that equation. Theta p plus theta m plus theta w equals to 0. So L square over 2ei minus ml over ei minus, right now you have WL cubed over 24ei. Okay, you need the ei here. Sorry, I missed it out. Equals to 0. Cancel, cancel, cancel. Cancel, cancel, and cancel. Alright. So again, PL is equals to 2m plus WL square over 12. This is the first equation we work on. Second equation, the delta equation. So we have PL cubed over 3i minus ML square over 2ei and minus WL to the fourth over 30ei. 0. Okay, so take this plug in this thing, this term here. So you get 2m over 3 plus WL square over 36 minus m over 2 minus WL square over 30 equals to 0. Okay. WL square on that side. 130 minus 136. 1 over 30 and 136. Okay. 360, right? So 36 minus 30 end up with 6 over 360. This is 1 over 60. Okay, for this side. 2/3 and then a half. Okay, so 4 6 and then the m over 6. Hey. 2 up here, right? Okay. What? Something. 4 6 3 6 1 6 130 and 160. Huh? Oh, but no. Okay. Got it. It is not 160. That's why. So 360. One is 12, another is 10, right? Okay. Okay. 2 over 360 equals to 180. Okay. So that makes your M equal to WL square over 30. Okay. If your M is equals to this, you plug in 115 plus 112. Okay. 115 and 112. So something over 120. 15 2, you get 30. 2 and then 30 multiplied by 4, so that's an 8. Right? 10 minus 8. Okay. Okay. Plus. Okay. 18 over 120. Okay. 320 WL. Wait, not square.
It's quite then.
It's square, but then it is cancelled out. Okay, at one point. So P is equals to 320 WL. Okay. Now, figure out the other reactions. So you have the P equals to 320 WL. You have the M being WL square over 30. Look at to the other side, you have a P downward, WL upward, okay? For this side, it has to be WL over 2, right? I didn't. Okay. And this moment is equals to 6. So WL over 2 upward and P being 320 pushing downward. So you have 720 WL upward. You determine the moment over there. PL, M, and WL square over 6. Okay, so that makes the 6 plus the M, which is 130, and then minus the PL. P is this one, so 320. So let's make it 60, okay? 10 plus 2 minus 8, 9, 3, 2, okay, 10. 12 minus 9, you get 3 over 60. WL square over 20. So, you now get the fixed end reactions accordingly. Go back, open the textbook to find this match with those things in a table. But at least I have a bad feeling when if I just open on the back of the textbook and then okay, just get this number. This is a fixed end reactions. Oh, we still have 20 minutes. Okay. Let me sit down. Now, fixed end reactions done. Okay.